All right, for those that are online, you can hear me okay and see the screen. It says chapter 8. Anyone? Think you can hear me? Okay, thank you, William. Okay. All right, so we are going to be moving to chapter 8. Okay. Okay, so on the unit 3, where's unit 3? There we go. There's this complex power, maximum power, and Fourier information. So this is going to be the sheet that you are going to be wanting. Will it open? Okay. So there's going to be these tables, just like there was for Laplace. These are the tables for the Fourier. And so you're going to have the same idea of what we did for Laplace, but we're going to do it now for the Fourier series and the Fourier transforms. So it has similar properties where if you multiply in the time domain, it's going to multiply it in the S domain, which now we're going to do. So what this is moving from S is equal to j omega. And omega is going to be a whole range of frequencies. And so we want to know from the Fourier more about the frequency ranges, frequency response. And so that's why we're doing it in omegas. And so these are all going to be f omega instead of f of s. And so properties, though, are very similar. You have a shift in time if you have the E in the omega domain or S domain. I'm still going to probably call it the S domain. So you analyze it very similarly. You have the transform, and then you just use the S in the analysis because S is usually easier than seeing j omega. And then you plug in S equals j omega at the end, and it's usually easier, and then you can transform it back. And so I tend to still use them in the S domain. Complex power, these are going to be the equations that we're going to kind of go through today, and the terminology is what we're going to be focused on, is what do these terms really mean, and then maximum power transfer. Okay. So those are the properties. These are the properties of the Laplace that we're going to need to do some of the manipulations. So just note that these tables are on the handout page just in the Unit 3 section. Okay. So when we talk about DC values, you think about DC as very flat, right? Like 5 volts, 10 volts. Now, when we talk about the AC and we talk about power in the AC, it is going to be varying, right? And so we need to come up with, if we have a sinusoid and we try and take the average of the sinusoid, what is the average of a sinusoid? 0. So 0 power doesn't make any sense. And so we're creating these new, or not, we're not creating them, they were created to have a new definition of average and RMS value. So that is where RMS comes from, is that we want to know, like, what does, if we do have a sinusoid, we know that there's power that's dissipated in a circuit. It's not going to be 0. And that's where the RMS value comes, is it is a way to give an average when you're talking about AC. Does that make sense? Okay. Hopefully that's a good enough description. So back to math, if you guys remember from averaging, if you have a continuous signal, you usually would take the integration of it over a time period to give you an average. You guys remember that? Okay. So that is what we're going to kind of look at. I like the definition that I use better as far as like the RMS is just going to be another way to say like for AC, that's our average value. Okay. Okay. So if we're looking at a signal such as this, and we do want to find the average and the RMS value of the periodic signal, like how do we go about doing that? So find my notes if I can get there. 2240. Pictures. Okay. All righty. So the VRMS, get up here, or maybe I'll do X. Okay, so this is the average one, and then the RMS one is going to be the square root of the average squared. So those are the equations that we're going to basically use. So root mean square. So that's where the root is the square root, and then the mean is average, and so then you square the signal. So RMS, root mean square.
You might be gonna go over this, but what exactly is like the circuit difference when you would use Fourier versus Laplace? Why switch?
We'll go over that when we get to the, so we first need to, we're going to go through AC power, which is chapter 8, and then we'll move back to the Fourier.
Okay.
So we'll discuss why. And yes, there is reasons why. Okay, so going down, let me copy these. So going down to this, we want to find this root mean square, and we want to find the average. So one, you got to see where is it periodic. So what would you say would be the period of this signal?
16.
Okay. So let's see. Make it here. Okay, so this is our period, T. Okay, and then we have kind of different descriptions here, right? Because this is, we kind of have to describe this as like a piecewise linear. So from 0 to 4. So we're going to kind of describe this signal. It's at minus 12 from 0 to 4, right? What would be the next section? How do we find this one? How?
Isn't it 3? Because it's like, yeah, no, it's different. Yeah, basic math. Yeah, okay. 3. If everything were equal to 1, then it's I see what you're saying. I do. Yes.
It intersects there somewhere. So you have to, do you remember how to find the slope of a line?
Rise over run.
Okay, there you go. Rise over run. And in this case, you go from
12 to 0 and 4 to 8. So it's 12 over 4.
correct. So you have a slope of plus 3 because it goes up 12 and then over 4. So how do you find, so what was the equation for a line?
Y equals mx plus b.
Okay, so y equals mx plus b. So this is our M, is the rise over the run. And then we need to find B. So we need to use the values that we have in this. So what would be our,
Negative 24.
What you said. Yeah. Agreed.
how do you find that negative 24?
Well,
You make your line.
So you know this point, right? 0 and 8.
so it would be,
So 0 is Y, 3, 8, plus B. So that's how you mathematically find that it's negative 24, if you don't see it.
It would be the other way around, 8, 0.
Yes, thank you. I wrote it backwards, 8, 0, yes. Y is 0 and 8, and X is Y. Oh my goodness, I can't talk, but yes. So from that, we can get that Y is equal to 3X minus 24. So that would be our minus 24. So this is the slope between 4 and 8. And then we would want to do the same thing for green. This slope, right, between 8 and 12. So what's that one going to be?
Slope is the same. Right intersection. 36. Make 36.
Correct. So this one is going to be same slope minus 36 between 8 and 12. And then it's again minus 12 from 12 to 16. So to find the average, we're just going to integrate and add all of these up. So I average will be 1 over 16. The first one, 0 to 4, minus 12 dt. And then 4 to 8, 3t minus 24 dt, plus 8 to 12, 3t minus 36 dt. Oops. And then 12 to 16, minus 12 dt. All right, so the integration of minus 12 dt is going to be what?
Minus 20.
And so 4 minus 0. And then the 3t minus 24. Three t becomes,
3 over 2 t squared.
correct. And then minus 24t, and then that's going to be evaluated from 4 to 8. And then the 3t minus 36 becomes
3 over 2 t squared.
correct.
Minus 36t.
And then evaluate that from 8 to 12. And then minus 12, 16 minus 12. And so, so 1 over 16 minus 48 plus 3 halves, 8 squared. Minus 24 times 8, minus 3 halves, 4 squared, minus 24, or plus 24 times 4, plus x 3/2 12 squared minus 36 times 12 minus 3/2 8 squared plus 36 8 minus 12 times 4. And so multiplying all that out, you get minus 9 amps. All right, then the IRMS is going to equal the root 1/16, and then all of these. I'm just going to copy them. Well, actually, I can't copy them.
Wait, why can't we just use the negative 9?
So that's the average, but the root mean square is a different value. So because the average is right in the middle of it, and then the average with the root mean square is a representation of, it's a better representation of the actual average of the signal.
Right, but isn't the t value the same, so wouldn't wouldn't we be able to just plug the I average into the square root?
No, because these become squared. So remember, it's 12 minus 12 squared dt. So,
Functions
yeah.
can be tricky when you square them, so you can't just.
Yeah. So this is where you're going to want to use a calculator instead of doing this part by hand. So using Wolfram, using some other calculator to do your differentiation, or integration, sorry. You should end up with 9.8 amps.
Why is there negative 12 squared in the first integral? Or,
So you take each piece of these. So you had negative 12 between
never mind.
0 to 4.
Yeah, that makes sense.
Okay.
I just forgot that there was a section right for the slope.
Okay. So the thing you can see here is like, yes, the average gives you like -9. Well, that makes sense because that's kind of here. Find a color. You know, like, yeah, that's the average if I was to look at this. So 9.8 is a representation of kind of, you're not including the negatives. So you're kind of incorporating the whole signal portion of it. So that 9.8 is a representation, a better representation of the actual value of the signal.
Can you scroll down to the,
Yeah.
How is it different? What allows, like, in the circuit, it to have an average that's not, like, just a mathematical average?
It's because you're taking the squared, so you're getting rid of all the negatives. So you're squaring all of those, and then you're taking the average of the squared of those. So you've, how do I describe this better? So yes, you're getting rid of all the negatives, but you have to take the square of it to get rid of those negatives. And then you're taking the average of the square part of it, and then the square root of it. So you're squaring it and then square rooting it. But that gets rid of kind of all the negatives. And so it gives you an end representation of that average better.
Okay,
Does that make
understand,
sense?
like, the math
Uh-huh.
of it, but I'm curious as to, like, why that makes sense, like, physically.
So you have, so what we want is kind of to say, well, in the DC, we have 5 watts of power here. And in the AC, when we put an AC signal on and it varies around that DC value, we want still 5, kind of 5 watts. So this root mean square gets us the closest value to that. If we take just the average, it gives us 0, so it doesn't give us that information. So this is just a way to compare it to a DC value. Does that help?
So do we need to know the average before we find the RMS, or?
No.
Okay, so we just use that technique with the equation squared to find.
So this one, yes.
Yeah, so instead of taking, for example, like -12 times from the integral 0 to 4 plus whatever, it would be -12 squared from 0 to 4? Okay.
So you're taking each portion, and if they're negative, you're squaring them to get rid of the squared.
So do we not square them if they're positive?
I mean, you still square them if they're positive, but that gets rid of that negative. So your value is always a positive value. And so you're just getting a quantity, and that quantity is representative of, and you're going to hear root mean squared everywhere. And so this is kind of what that root mean squared means, is just an average of an AC signal to give it a representation to be able to compare it to a DC value. Hopefully that makes sense. Yes.
So it's kind of like magnitude. So if you had like that same wave but positive, the average would be 0, but that root mean square would be about 9.8 still.
Yeah. So it gives you more information about a sign, like any repetitive signal. And you can even, you can use now, oscilloscopes will do like the root mean square, so you can actually like have a chaotic signal that you don't see exactly where the periodicity is, and it will calculate a root mean square for you. And again, that's just giving you an average value of what your signals are. So that gives you an idea, like, okay, if you have a lot of noise and you do take the root mean square of that and you're like, oh, it's 1, that's showing you like, oh, that's quite a bit of noise in there. If it was like 0.001, you're like, oh, that's really small, but if it was 1 volt. So that helps you kind of quantify chaos and noise, and then also it gives us a frame to be able to represent sinusoids when, the average parts of it would be 0, which doesn't make sense when we're trying to find like complex power, which is what we're moving into. Does that kind of help you grasp your head around what this term means? Okay. So mathematically, that would be how you would calculate it. Okay, so go ahead and work on this one. Find the average and the RMS value of this waveform. Okay. Let's see, so VFD. Okay. So, hopefully you found that the slope was 3/2. So from 0 to 2, it's 3/2. And then 0 from 2 to 4. So plugging that in, you have 1/4, and integrate it from 0 to 2 of 1.5t, which becomes 1.5t squared over 2, and evaluate from 0 to 2, and gives 0.75 volts. And then for the RMS, it's 1/4 and then 1.5t squared, and so 1.22 volts.
Oh, was the average?
1.5 also gets squared.
Yep, 1.5 squared is in that 2.2.
But then that would also
Oh,
be divided.
wait.
Because it's that the whole thing squared.
1.5 squared is 2.25. So this is 2.25 t squared. And so you have the 2.25, and then the t squared becomes t cubed over 3. You look like I lost you for a minute.
No, I'm just trying to figure out where I'm wrong now, because I got 1.5. The square root of 1.5 or the square, yeah, the square root of 1.5.
So 1.5 squared is 2.25.
And that is 1.25, I got the square root of that. I'm pretty sure I did all the same steps. Never mind, I'll come up with this out.
Okay. Any questions on this?
What did you get for average?
0.75. Draw my voltmeter. Okay, so average RMS. Now you're looking confused.
I'm just really amazed that I'm so static. Crazy math. That's okay. Wait, hold on. How do we get I'm there.
Okay. Give you guys a second.
That is so weird. I gotta have a different number. So with the 1.5t squared, it would be 1.5t to the third divided by 3. You wouldn't necessarily square both of the insides together.
Don't know what you mean by insides. So this will be 2 cubed over 3, and then the 0.
That's what I mean. So because that's a polynomial, you take that number 1.5t, and because the 2 is on the outside, when you take the integral of that, you take the integral of the whole thing. So that goes to a 3, and then you divide 1.5t by 3. So it's 1.5t cubed divided by 3. So the 2 will be cubed, or the 1.5 will be cubed at the end, instead of squaring it and taking it out, which will give you a different number.
No, because so it's like, so if I have 2t squared, I don't raise this one to, because that's a constant, so you always have to bring the constant out first. So I'd take 4t squared, and then this is what gets integrated, not the constant. You don't integrate the constant.
You integrate the equation, don't you?
If it's a like x minus 1 squared, then that quantity you do, but because this is a constant in the front, you don't. So if I had like 2 minus t squared, then I would have to take that and raise it all to the third and then divide the whole thing by the third. But that 1.5 is a constant. So you bring out all the constants from the integral. Does that make sense, Bri? Okay, I can talk to you more about it after if you want. Okay, next part of this is some new terminology. So we're moving to complex power now. So we're going to talk about average real power and reactive power. And so these terms,
Even still, that gave me 1.5 when I plugged it into symbol out. So I'm not sure where the 1.22 is coming from.
I'm getting 1.22.
1.2 is a square root of 1.5.
Oh, that's fine.
thank you. Okay, we're good now? Okay. All right, so, all right, now looking at this, we know that the power, how do we find power?
IV.
Thank you. I times V. And we do the same thing when we're in a AC. So we would take the current 3 cosine 377t minus 30 degrees and multiply it by the 4 cosine 377t plus 30. Okay, ran out of space. If you recall, there's a property, cosine x times cosine y is a half cosine x minus y plus a half cosine x plus y.
Where would 3 and 4 go? Would they just be multiplied out by 12 in front of the whole thing? So it would be 12 cosine x cosine y?
Yeah. So, yeah, we would have 12, and then we would divide it by 2 for the first one, cosine, and then x in this case. So this is x minus y, and this is x plus y. And so we would,
Wait. Wouldn't 377t minus 30 degrees be x and 377t plus 30 degrees be y?
sorry, thank you. I am like, yeah. Sorry, this is x, this is y. Oh my goodness. Okay, so this becomes 377t minus 30 degrees, which is x, and then a minus y. And then 12 over 2 cosine, and then x again, 377t minus 30, plus the 377t plus 30. So,
377's cancel out in the first one and 30 degrees cancels out in the second one.
oh, sorry, this is a plus there, because, wait,
No, I was right.
yeah, you're right. So,
6 times cosine of negative 60 degrees.
thank you.
And then 6 cosine of whatever 377 times 2 is, t 2.
So, so if we want to kind of write this in generic form, this was like the magnitudes of I. So this was I. So the IM is the magnitude, and the VM, which was the magnitude. So both of those were multiplied and then divided by 2. So that was this portion here. This one was taking the 30, which was the angle here. Let's see. So theta I and theta V. And so theta V minus theta I. And then this portion was 2 times that omega t. So notice that we're taking the average would be integration of a cosine, which puts this one as you integrate it to 0. These is just values, and it doesn't have any t's to it, so it becomes a constant. So you just bring that out, and then the 1 over t, so this whole portion is a constant here. And so it just becomes that value times t over t. And so this is actually your average value, is that you just take the magnitudes divided by 2 and then cosine of their angle difference. Yes.
I got distracted halfway along. But, so we're saying that it's cosine of theta V minus theta I.
Uh-huh.
When we did it, I think we just did our x's backwards. So we got like a negative 60,
Yeah.
right? Whereas that one would have given us positive 60.
Yeah.
No, it would be negative 60.
So is it V
It's
minus
negative
I?
30 minus 30. So the first angle is a negative angle and the second one's a positive. So it's subtracting a positive from a negative, which just gives a larger negative.
Right. So if we do V minus I, we get positive 60. But when we did the math, we did I minus V. Because we did X minus Y.
Yeah, that would give you a positive 60 if you did it the way around.
Yeah, I'll have to think about that one.
Okay.
I'll have to think about that one, because yeah, I did do it backwards
It's the
there.
same though. I think
It should come out the same, whether you multiply it.
60, so.
So I must have had a negative sign somewhere.
that it works out. I just wanted to know, like,
Yeah.
something gets flipped.
It should work out either way, whether you're multiplying it first or last. Yes.
How do we know that that cosine section is for sure going to 0?
So cosine to t, because the others are just shifting it. Cosine 2t, it just increases the frequency. So it doesn't increase the amplitude. And so when you integrate cosine, it's always 0 over a time period.
T is like a period of
Yep.
cosine?
Yeah, t is the period. So if you're doing it over one period, you're for sure just 0 because it goes up and down. And 2t just increases it in between that time period to twice that. So it's exactly 0 still, though.
Would there ever be any difference in frequency between the voltage and current? Would those always have the same frequency, just be phase shifted off each other?
So how do I describe this? So yes, they'll have the same base frequency. So it depends on your inputs. And so usually you just have one input source that has that frequency, and then the rest of the circuit has that same base frequency. 3500, you get into when you don't have just one frequency in there. But the ones we were looking at, we're only going to look at one frequency.
Okay, so that's for now, they have the same frequency.
For now, they have the same frequency, yeah. That was why I hesitated, because you can have systems that have different frequencies, but we're only going to look at the ones with same frequencies.
That's a problem for future meetings.
Correct. Okay. All right, so complex power, we just looked about the average one. So now RMS is going to give us some new terms. So we can describe the RMS of any signal. The nice thing is that integration actually always comes down to this. So it's always the magnitude, that Vm over the square root of 2, Ej to whatever the phase shift is. And IRMS is going to be the same. So that's kind of a nice value that is easier to work with. We're going to term this complex power as a capital X, S, complex power. So S is going to be the notation for complex power, capital S. And when we do, when we multiply these out, the result is taking the VRMS times the complex conjugate of IRMS. Do you guys remember what the complex conjugate means? Anyone want to share? Go ahead, Marley.
You just switch the like one negative positive sign into that.
For J's.
Yeah.
Yep, just swap J. So the complex means a positive J goes to a negative J, and a negative J goes to a positive J. Yes.
I'm sorry, I forgot. What is the difference between EM and EN?
Sorry, which one?
Oh,
Oh,
the magnitude?
yeah, VM is the magnitude or the amplitude. All right, so the new terminology, so this apparent power is the magnitude of this complex power. So this is a term you need to memorize what it means. Apparent power is the magnitude. We have what's called this power factor, and it's this cosine of the difference between the phase shift from the voltage to the current. And then we have, so when we put the complex power in what do you call it, polar form. So this is polar form. That magnitude is the apparent power. When it's in rectangular form, you can look at the two values for the average, and we can get the average actually that way instead of doing the whole multiplication. And so this is average absorbed power, and then we have reactive power. The reactive power is the imaginary portion of that rectangular form. And you're going to love this, is we have new units. So, average power, because it's real, is in watts. Reactive power is volt ampere reactive, VAR. And complex power is VA, volt ampere. They all mean power. But they're different units. Okay, so we will work through problems next time. So try to figure out what these terms now mean.
What was the P and E again?
P average is in watts. That's the average power. So that one stays in watts.
What the heck is the reactive?
So reactive is your complex power portion,
But why is it called reactive?
because it's imaginary.
Why is it imaginary? Okay, so for the average absorbed power and the peak exchange power,
Mhm.
we're just saying that it is like the real or imaginary portion of S.
Yeah,
Okay.
yeah. So that imaginary value in front of the J, that's your Q. That's going to be the reactive peak exchanged power.
So what is the average absorbed power?
That's the same as we,
Power? Or
it's the same that we just calculated up here, but it's just another way of finding it from
just the
IRMS.
the average?
What?
So just the I average and the average?
Over 2 times cosine theta v minus theta I. But it's easier to do it in polar form multiplications. And so this is another way of getting that average power instead of taking the cosine. Just do it in polar form, multiply them out, and then you can easily find that average power from there in rectangular form. Does that make sense? It will make more sense when we actually look at equations, and it makes it easier to find this way. But it means the same thing that we found before in the time domain when we multiplied those two cosines. This is just way easier to multiply E because you just add those angles together.
How are we able to model something real like power with imaginary numbers?
So remember that the S domain is there to be able to give us a way to like multiply like these. So it's not a real plane. It's a way of manipulating the equations where we don't have to multiply all those cosines out. So I can change it to E. So it gives us a way of adding instead of having to multiply cosines and so on. So it's a way of just making the math way easier to do.
Okay. So that's why we go into imaginary and then out of
Yeah,
imaginary.
correct.
All right. That makes sense.
So we've moved to imaginary here by moving to the polar forms. And then the values will then, the magnitude stays the same in the imaginary, in the S domain kind of thing, and in the real world. So it gives us real values. All right, we'll see you guys on Monday.
Tuesday?